Okay, we're at the top of the hour, so here we go with session 2 of day 2 of the 2025 RNG Technical Symposium. I'm Paul Green. I run a biogas advisory business, and I drive the website biogas.tv. In this session, we're going to hear from Mainspring about linear generators. You can ask questions on the fly in the chat or the Q&A box, and we'll spend a few minutes on questions at the end. Later today, you'll get an email from me pointing to the slides from this talk on my website, and a video recording of these sessions will be available on biogas.tv by the end of the week. With that, I'd like to introduce Kyle Plaster. He's going to talk to you about biogas to power linear generators. So, Kyle, go ahead. The floor is yours.
All right. Thank you. So first, I just want to thank everyone for being here. Thanks to Paul for setting this up. I think this is a great opportunity to talk about different technologies in our industry. As Paul said, my name is Kyle Plaster. I've been in biogas for almost over 6.5 years now. I actually started in the RNG upgrading space and have transitioned over to power generation. So now I'm with Mainspring Energy. Mainspring is a provider of linear generators. Linear generators are a form of power generation technology. And yeah, excited to talk about this with you guys today. So a little bit about Mainspring. Mainspring has actually been around since 2010. From 2010 to 2020, we were really just focused on research and development. Most of that research and development was focused around software and control of our system. We have oscillators or pistons that move back and forth, so a lot of that R&D was focused around the control of that. Starting in 2020, we began commercial sales, and since 2020, so it's been a little bit over 5 years, we have over 60 units deployed in the field. So we're expanding very, very rapidly. I'll talk about some of the case studies later on at the end of this presentation, but as you'll see and pick up that we are expanding quite fast. If you look at the bottom, you'll see some of the investors that we have. So we're very financially sound. And then I'll talk about this in the next slide, but we've got quite a few blue chip customers that a lot of people I'm sure would recognize. So if you look at the left-hand side, that is our footprint. You can see we're coast to coast. It's pretty evident we do very well where power is expensive. So that's why we have a lot of deployments in California and the Northeast. But as you can see, we also have projects in the middle of the country as well. If you look at the right-hand side, you can see some of our customers, Lineage, Prologis, cold storage and logistics companies, Kroger, Meyer, Home Depot, UPS, FedEx. A lot of these customers very recognizable. We do a lot of projects. So I should back up a little bit. In Mainspring, we can handle pretty much any gas fuel type. And a lot of our projects are pipeline natural gas, propane, and stuff like that. Of course, today I'll be focused on the renewable side of things, biogas, syngas, hydrogen, and even green ammonia. With that being said, we've got quite a few biogas clients as well. So if you can see, again, on the right-hand side, California Bioenergy, we have several biogas to power projects with them, of course, in California, and then Napa San as well, which is a wastewater treatment plant. We also have a biogas to power project with them. Within biogas, we've actually hit on every sub-segment. So we've got projects with dairies, landfills, wastewater treatment plants, and we even have some running on food waste. So we're very well versed in the biogas world. To meet that increased demand that we're seeing, we're ramping up production quite significantly. We've got a large manufacturing facility in Monterrey, Mexico. We also have a manufacturing / research and development facility in Menlo Park, California. That's where we're based. And then we're actually constructing a facility in Pittsburgh, Pennsylvania to meet the increased demand that we're seeing. If you look at the picture, you can actually see one of our cores. There's 2 cores in our units. So in each core produces 125 kW, but it's a good representation of the internals of the system, just to give you guys an idea. So how the system works is actually pretty straightforward. If you look at the screen, that's one of the cores. This is what you were seeing on the last screen. And again, it's pretty straightforward. If you look at the center of the screen, you'll see the reaction zone. On the right-hand side of the reaction zone, you'll see those perforations. That is actually the intake. So we have a mixture of fuel and air that enters from the right-hand side there. And then the left-hand side is the exhaust. So the intake and the exhaust happens at the exact same time. As those oscillators come together, it closes the intake and the exhaust and creates a high pressure in the reaction zone. This technology is non-combustion. There's no spark plug. It's actually compression triggering a oxidation reaction. Of course, once the chemical reaction takes place, there's an expansion. It pushes these oscillators out onto the air springs. The air springs themselves gain pressure and then push the oscillators back together to complete the cycle. The whole reason we do this is to be able to control the temperature of the reaction zone. We cool the reaction zone to be below the temperature in which a lot of those nasty pollutants form. So without any post-gas treatment, we have the same emissions profile that of a fuel cell. We have extremely low NOx, carbon monoxide, VOCs, and very low CO2. And again, this is without any post-gas treatment. We're also very highly efficient. So the reason we're able to achieve such high efficiency is we're directly converting this linear motion you see on the screen to electricity. So these oscillators, they have magnets on them, and the magnets are wrapped in copper coils. You can see the copper coil stationary there. And if you move a magnet through an electromagnetic field, you'll produce electricity. So again, that's why we're able to achieve such a high efficiency. Our efficiency is around 46%. So pretty much the same emissions and efficiency that of a fuel cell. The difference, of course, is that we are a generator. So we're highly dispatchable. We can ramp up, ramp down to follow any load curves. And we can basically get from 0 to 100% output in less than 10 seconds. A few other very cool things about the system. So we can actually handle different fuel types, gas fuel types, and we can handle those different fuel types on the fly. So for example, a customer could send, biogas to our system and then immediately switch over to green hydrogen, for example, and we wouldn't have to change anything to the system. Basically, without any software changes, the system can automatically adjust, and it's because we have sensors internal to the reaction zone that can sense the compression ratio needed to get to that oxidation reaction. So again, without any software or any changes to the system, we can handle different fuel types. A few other things. So the moving, or what you're seeing on the screen, is pretty much the only moving part in the system. So with that being said, we have extremely high reliability and high availability. Also, we have no oils or greases in the system at all. So the only lubrication we have in the system are graphite seals that we put at the ends of both of the oscillators. So we can basically keep the reaction zones and the air springs airtight. With that being said, the only short-term maintenance we really have in the system is replacing those graphite seals. So O&M is extremely, extremely low for us.
Kyle, one quick question came in. What about ammonia as a feed source? Is that viable?
Yeah, that's actually what I'll talk about in the next slide, but we do a lot of green ammonia projects as well.
Cool.
A few other things. So again, no oils or greases in the system. We actually have air bearings that will keep the oscillators elevated off the surface of the core. They just shoot out high pressurized air. I think that's good for this slide. We'll go ahead and move on. So same diagram. This is again talking about fuel flexibility. So as I said in the last slide, we can handle different fuel types and we can handle switching between those fuel types on the fly. So the example here is methane, hydrogen, and ammonia. This is especially important if any client has a biogas project in which the feedstock's changing and therefore the methane percentages are changing. We could handle that adjustment on the fly. It's also very important for syngas projects where they have a large list of constituents in the gas. And if anything changes with the feedstock, then those constituents can change. Of course, again, we can handle that change on the fly. If you look at the bottom here, this is a few other examples. The lighter blue is Mainspring, the darker blue is Grid. So if you look at the left-hand side, you'll see that we can ramp up and ramp down to meet pretty much any load curve out there. And this is an example of us being prime power in this case. In the middle scenario, we're basically getting a constant electricity or power source from the grid, and we're able to peak shave when the site has peaks in power demand. And then finally, we can also do backup power. So if you look at the right-hand side, you can see the grid going, coming off, us coming on. And again, we can get from 0 to 100% in less than 10 seconds. So we can easily meet that backup power demand. And then as you can see, the grid comes back on and we shut off. Really what I'm trying to say with this slide is our technology is very versatile. We have many different use cases, not just within biogas, but also outside of biogas. All right, so a little bit more about the product. If you look on the right-hand side here, that's what the units actually look like. So it's about a 20-foot shipping container. If space is an issue on site, we can actually stack units. So it's something that we usually can get around very easily. I already talked about this quite a bit, but again, we can switch between fuel types on the fly. Cleanup is very minimal for our system. So the example I like to use here is biogas. But the only things we'd like to or need to remove from the system or from the gas would be H2S, siloxanes, and then moisture above 70% relative humidity. So usually coming out of a digester, what we would expect is a dehy and boosting skid, and then an activated carbon vessel for H2S removal needs. Resiliency, so we can be grid parallel or island operated. If we were island operated, we'd simply have a battery internal of the system that handle the startup power needs. Easy to permit. So even though we are not a fuel cell, the US likes to categorize us as a fuel cell. So with that being said, we're very good at permitting, and we excel in places where it's hardest to permit in the country. So we've got a lot of projects in California in the Northeast, projects within California in the San Joaquin Valley and North Coast. So wherever it's hardest to permit, we do our best work.
Kyle, quick question on noise levels, decibel levels.
Yep. So we're at 80 dBA at 3 meters. So pretty standard when it comes to power generation technology. I've stood next to these units while they're running. It basically sounds like a washing machine. So it's very, very quiet. Easy installation. So of course we're UL listed, and then we've got grid tie-in inverters, so we can tie into pretty much any grid out there. And then finally, CHP potential. So we're in the process of developing this right now, but we should have it commercially available very soon. But basically, even though we cooled that reaction zone, we still get a very, very hot exhaust gas. And we can simply install a gas to liquid heat exchanger and then send hot water to a digester, for example. Like I said, we're in the middle of developing this, and we've already determined that we can basically offer about 0.32 MMBTU per unit per hour. And if you've got one or even multiple units on site, that's plenty to heat a digester. So that's about the product. I don't want to get too salesy, but I do want to talk a little bit about our services. Before I go into services, I just like to mention that even though we're a startup, we are quite large. We have over 450 employees. And with that being said, we have a lot of departments internal that can handle a lot of the project needs. For example, we've got a very robust air permitting, electrical interconnect, and even gas interconnect team. As you can see down below, we can even offer EPC. A little bit more about O&M. So it's a very low cost, but the real benefit is that it's a full wrap of the system for planned or unplanned maintenance. And that's really just because we're so confident in our technology and willing to stand by it. So when you look at our technology, there's a lot of different benefits: fuel flexibility, low emissions. But from an economic standpoint, the real reason a lot of people use our technology is the high efficiency and the low O&M really drives down our total cost of ownership, especially when compared to other power gen technologies. Moving on. So in this slide, I just want to talk about the different use cases within biogas. Of course, the main and most predominant one we have is biogas to power. Usually when we're doing biogas to power, it's either an isolated digester. So RNG is not usually an option if it's isolated, not near an injection point, or it's a smaller biogas to biogas project where RNG doesn't make sense, things like that. Most of the size biogas projects we deal with are in the 200 SCFM or lower range, but we have projects that go all the way up to 5 and 10 megawatts. So we deal with some very high gas volumes.
To that point, Kyle, a question came in. The largest size of one single machine is how big?
We only have one size right now, and that's 250 kW. But again, we can, install as many units as needed to meet power needs.
Yeah, the
I will
question
say,
is, oh, sorry.
no, go ahead.
Question on balance of plant needs. So do you need a recuperator, cooling water? What other balance of plant type of things are required?
So all cooling, everything like that is internal to system. So they wouldn't need that. Again, the only thing you need to hook up to is the gas inlet, and then there's electricity output. And the only treatment of the gas, at least if it's biogas, would be H2S removal, siloxane removal, and then moisture removal if it's above 70% relative humidity.
Okay.
So pretty straightforward. But everything's internal, so you wouldn't have to worry about that. Talking more about biogas to power, so we see kind of two different use cases. We see a lot of greenfield and a lot of brownfield. Again, greenfield is going to be those isolated digesters or smaller plants. Of course, we can take that excess biogas and then use it either to power the site or export it to grid. Again, we usually do these projects in places where electricity is very expensive, so that either you're avoiding paying, for example, PG&E a lot of money for the electricity, or you're exporting that electricity and getting a good payback for it. Outside of greenfield biogas to power projects, we also do a lot of brownfield biogas to power projects. These are usually existing RNG sites where biogas production is cyclical. So a good example I like to use is maybe during the summer, if ambient temperatures are very hot, you could produce even more biogas than the RNG system is capable of, injecting to the grid or processing. We'll take that excess biogas, again, usually during the summer, install some of our units, and then power the site or export to grid. So those are most of our biogas to power projects. Again, usually they're either greenfield or brownfield. Outside of biogas to power, we still do a lot within biogas. We actually do a lot of powering RNG sites with pipeline natural gas. So funny enough, the example project that I believe Timur had on the last slide that Pax was talking about with Moss, we installed a unit. It's going to be running on pipeline natural gas, and it'll actually power that site. So that's that 5-point site. We do a lot of this, and again, usually in places where electricity is very expensive, so they can avoid paying high utility costs altogether. Next use case I like to talk about, this is more of a niche use case. So again, the only things that we need to remove from the gas are siloxanes and H2S. So with that being said, we can handle high levels of VOCs, carbon monoxide, nitrogen, oxygen, pretty much anything else in the gas. So we actually do a lot of thermal oxidizer and flare replacement, basically just because we can do exactly what a thermal oxidizer or flare would do, which is to destroy all those nasty constituents in the gas, but we can also produce power for the site. So that's kind of all of our use cases within biogas. Of course, outside of biogas, we deal with other renewable fuels such as syngas, hydrogen, and ammonia, but that's, I guess, for another presentation. So here are our specifications specifically for biogas. Methane would need to be at around 35%. Again, relative humidity below 70%. Sulfur, we can actually handle up to 30 ppm, so that's usually higher than other power gen technologies. Siloxanes, non-detect limits, so that's about 100 parts per billion. Oxygen and nitrogen, no limitations. Of course, we still need to get to that 35% methane, so as long as we're getting to that 35% methane, no limitations there. And then finally, gas pressure, 10 to 25 psig. To give you guys an example for gas pressure, if you had 60% methane biogas, we would only require 10 psig. So usually we can be below that 15 psig for pressure rated vessels.
Getting a lot of engagement. Hope you don't mind my interruptions
Go
here.
for it. Go for it.
Okay, so a few here. Ballpark, how many SCFM of biogas do you need for a 250 kW unit?
So it takes 60 SCFM of 60% methane biogas to get our full output of 250 kW. Yep.
What would be the LCOE running on purchased natural gas?
Purchased natural gas, I would have to look because it can vary, depending on how expensive the gas is. But we're roughly around that 10 to 12 cents around there per kilowatt, that is. Yeah.
On scalability, do you need or design the paralleling gear?
Yeah, we do. I mean, we'll talk about some larger projects when I get to case studies, but for example, we just announced a 50 megawatt deal for a data center, and we'll be doing a lot of that, of course, to make sure the site runs properly.
What does the typical overhaul or major replacement duration, what does that look like?
So we have short-term maintenance, which is really replacing those graphite seals. That's like 3 to 4 hours. I mean, actually keep one core running and one core off, so you can still run 125 kW. For the long-term maintenance, that's usually just one day down, 8 hours of maintenance, and that's only every 40,000 hours.
I think that's the question. So every 40,000 hours, you need an overhaul?
Yes, and that's only an 8 hour overall. And it's not, we never would need to replace a core. These units have a 20-year lifespan. It would just be dealing with other long-term maintenance.
Okay, we're caught up.
All right, great. Yeah, keep the questions coming.
Yep.
All right, moving on. So here's a comparison on emissions. This doesn't have CO2. I'll talk about CO2 on the next slide. This is predominantly focused on NOx, carbon monoxide, and then VOCs. If you look at the right-hand side, you can see engines are, quite dirty. Micro turbines are a great improvement, but still, a lot of emissions. And then, of course, mainspring and fuel cells, pretty much zero. So very, very low emissions. Moving on to CO2. Of course, if you're running either mainspring or fuel cells on hydrogen, you're going to get no CO2. Running on natural gas, as you can see, we're right around fuel cells, just a little bit above. And then engines and micro turbines are a little bit farther up. So here's a direct comparison. This is no knock on other power generation technologies. I think power generation is a lot like RNG upgrading, where technology is really, or technology selection is dependent on the project, and there's different use cases for different technologies. So I'll just really focus on linear generators here. Again, 250 kW is our size. We only have one size at this time. With that being said, we do have plans to increase. We're not going to get smaller. If anything, we're going to get larger. That's still a ways down the road, but we do have plans to have larger sizes eventually. Efficiency, again, 46%. So we're a little bit below fuel cells, but of course, much better than microturbines or engines. Again, the biggest difference between us and fuel cells is that we are dispatchable. We can ramp up and ramp down. We can follow load curves, and we can get from 0 to 100% in less than 10 seconds, as you can see down below. Fuels, again, we can handle different fuel types on the fly. Output range, we can get all the way down to 1%. So we can go as low as needed as far as derated capacity. So basically can go all the way down, and again, can get from 0 to 100% in less than 10 seconds. I already mentioned emissions on the last couple of slides, but here's a direct comparison on the NOx emissions. So this is a cool slide, I think, to compare a lot of technologies. And again, no knock on other technologies. I think there's different use cases for different projects, and different technologies are more suited on a project by project basis.
Question for you, Kyle. So what about how much waste heat is produced that could be used and recovered, and at what temperature might that be at?
I don't have the exact temperature on the top of my head. Like I said previously, when we were talking about 8 CHP, we do get a very hot exhaust gas, and we are in the process of capturing that. To give an actual figure here, again, we were able to, per unit per hour, it's around 0.32 MMBTU we're able to capture. So we're in the process of developing that CHP, and we'll be able to offer that per unit, I'm sure, very, very soon.
Another question. The attendees observing that ammonia is poisonous to fuel cells, so that's not an issue for your unit?
Not at all. Not at all. We've done a lot of testing on ammonia, and we're even able to be below, NOx levels requirement for air permitting when running on ammonia. So that's not an issue.
Okay.
All right. So that was about the product, about Mainspring, kind of how we got here and where we're going. Now I'll talk about a few case studies. The first one I'll talk about is CalBio. So CalBio is a good example of a brownfield RNG system. So they had an existing RNG site. They were producing a lot more biogas during the summer. This project's located in Central Valley, so as you can tell, ambient temperatures vary quite a bit. So during the summer, they were producing almost 200 SCFM more than during the winter, and they were actually flaring that gas. So they came to us, and we decided to install 4 of our units, so 1 megawatt of our linear generators. And we're, instead of flaring that gas, they're producing power for the site, and I actually believe exporting a little bit as well, just because we're able to not only meet their power needs, but able to export some of it too. So a good story, a good use case. And we've actually have quite a few projects with CalBio and a lot of other large dairy developers within California. Another use case that I've already talked about a little bit is the Napa Sanitation District. So this is the wastewater treatment plant in Napa Valley, California. This site was already producing biogas and using it in a few CHPs, but they were still needing to pull some power from the grid in order to meet their full power needs. They were still, although, also producing biogas and still flaring it. So they wanted to do something with the biogas in order to avoid using the grid. And they were also getting a lot of grid outages, and they didn't want to deal with that, especially as a wastewater treatment plant. In order to meet the full power needs, though, they needed something very, very efficient. So they decided to install one of our linear generators, and now are completely independent of the grid and don't have to worry about grid outages. So another good example of using our technology within biogas.
Two more questions. What is the operating temperature of the unit?
I got to say, I don't know that in the top of my head. Again, though, we have these units out and the exhaust just comes right out the side, and you can put your hand up to it and it's not hot. Of course, inside the unit, the exhaust gas is much hotter, as we have cooling inside the unit that takes care of that. So it can just be released from the side of the unit, but I don't have an exact figure in the top of my head. Yeah.
Next is, what is the production wait time?
We just have a 9-month lead time right now.
Okay.
Yep. And then finally, we've already talked about dairy gas, wastewater treatment gas, and now let's talk about a little bit of landfill gas. So this project actually made it on the news, as you can see on the left-hand side, screenshot we have. So in this project, we basically just took landfill gas and produced power to power the site. This was a pilot project, actually, so we ran this for about 3 months. But again, kind of showed that we could run on landfill gas, a very dirty gas, especially dirtier than the other kinds of biogas. And we didn't have to do any further pre-treatment of the gas other than siloxane and H2S removal. So it was a good use case for us and shows that we can handle some of those nastier pollutants in the gas very easily. Then finally, I just want to talk about a few biogas adjacent projects. So this is not a biogas project, although we have done other biogas projects with California dairies. In this case, they needed something to power their bottling facility. So on this project, we're actually taking pipeline natural gas and powering the site. The reason they came to us is they needed something, 1, very efficient, and then 2, low emissions, because it is based in California. So easy to produce site, and they're avoiding, the high cost of electricity in California, and then also producing a low emissions electricity. And then finally, again, outside of biogas, I just want to mention that we're doing a lot of projects, not just in biogas, but in data center, pipeline natural gas projects and stuff like that. So we just announced a 50 megawatt deal with Xcel Energy. I'll let you guys do the math, but that is 200 of our units. So when I say that we're expanding rapidly, I mean we are expanding very, very rapidly. We've got a few of these data center deals, and this is just to show that we're not just in biogas. We have a lot of different industries that we're tackling right now. But all right.
Sounds good. So last
Yeah.
question in the door was pertaining to landfill gas, and landfill gas can be pretty fickle, pretty dirty. Have all of your landfill installations been successful? What kind of things come up that can be problematic about landfill gas?
So really the only issue we've had is if anything condenses in the unit. So we just have to make sure we can handle pretty much in the gas as long as nothing condenses within the unit. So that's a big reason why we do the 70% relative humidity. But if we have anything in the landfill gas like long carbon chains or anything like that, we would just need to make sure it doesn't condense within the unit. But aside from that, we've really had no issues.
Okay, do you provide vibration probes with the machine, presumably because of the reciprocating linear operation of the shafts?
So because the oscillators are coming back together and they're kind of opposite of each other, and we also have two cores within the unit, we really don't have too much vibration because the cores kind of offset each other. So I'm not exactly sure if we have vibration probes, but I know from seeing these units installed that we don't have much vibration, and usually it's not something that we need to tackle.
Okay. All right, last chance for questions, friends. Otherwise, we'll let Kyle be on his day. So we're caught up. Kyle's slides will be, Kyle, I do not have your slides. If you want them for download, make sure to send me a copy. But next conversation is at the top of the hour. We have Virgin Power Solutions talking about landfill gas and capstone microturbines. So thank you all for joining session 2. With that, session 2 is a wrap. Thanks, everybody.
Thanks, everyone. Yep.